difficulties. Okay, we will discuss that whatever the internal questions and answers. Okay, once again, welcome you all for this online class. Okay, we'll start the lecture by uploading this presentation. Okay, this presentation is visible to everyone.
Yes, sir.
Okay.
Você, soro para 15. ಈಗ ಮತ್ತೆ ಫೋನ್ ಹಚ್ಚಿದ್ರೆ ನೀವು ನೀವು ಹಚ್ಚಿದ್ರೆ ಏನಾಗ್ತದೆ?
Hello? Hello? Hello?
Hello, sir.
Am I audible? Okay, it was, I think, disconnected when we started the explanation. Where it was disconnected, have you noticed? I think nobody was
Yes.
intimated with respect of this disconnection. Huh? Where it was disconnected?
From the beginning, sir.
From the beginning only it was disconnected. You have to intimate, no? You have to intimate. Okay, we will start once again, no problem. Okay. Okay. Here we are taking the three cases for our discussions, case 3, case 4, case 5. In this today's class, the case 3 will be the two isotropic point source of the same amplitude and in phase quadrature. Okay, the phases of the
So we can't
source.
see any screen.
Yeah. 3.
So we can't see any screen being shared.
Okay, okay, okay.
And even the chat section is blocked. I mean, we cannot text anything to tell you what is the error.
Okay, okay, okay. At least you have to message, no?
Yes, sir.
Okay. Okay, understand here very important part of the discussion, how you are considering the antenna. Okay, how it will be in the far field distance. What will be the angle by the source 1 or what will be the angle by the source 2 in the far field distance. With respect to of that, we have the field pattern in the far field distance. We have the field pattern in the far field distance. Okay, is it visible?
Yes, sir.
Okay. Here the two isotropic point sources of the same amplitude and the in phase quadrature. What is the in phase quadrature? In phase quadrature is nothing but the source 1 will be retarded by the 45 degree and the source 2 will be advanced by the 45 degree. Okay, therefore, so by the origin, from the origin, okay, how the sources will be, okay, considered in the far field distance, how the sources will be appear in the far field distance. With respect of that, the field will be analyzed. Source 1 will be 45 degree and the source 2 will be the 45 degree. It is the advanced, that is the source 2, and the source 1 will be the what is the retarded. With respect of that, the field will be analyzed in the far field distance, that is with respect of the r distance. R distance is nothing but it is the radial direction. The field will be observed on the radial direction. Therefore, the E will equal to the E naught. E naught is the magnitude will be the same. Why? Because the two isotropic point sources of the same amplitude. Amplitude we are considering is the E naught. And the field experiencing in the far field distance, that is the exponential plus j dr cos pi divided by the 2 plus pi by 4 plus pi by 4. It is with respect of the source 2 and is with respect of the one source 1, it will be the minus. Okay, that minus is indicating, minus j is indicating it is the retarded, plus into the exponential j dr cos pi divided by the 2 plus pi by 4. Therefore, you simplify this equation by taking the E naught outside. Simplify this equation by taking the E naught outside and multiply again after simplification by the 2 as well as the divided by the 2. Multiply 2 divided by the 2, you will get the equation, simplification equation E equal to the 2 E naught cos of pi by 4 plus the dr by 2 cos pi. Pi by 4 plus dr by 2 cos pi. What is the dr? Dr is the distance. Distance with respect of the radial direction. Therefore, the dr which is equal to the 2 pi divided by the lambda into the d. This distance will be what here the mainly, okay, or it is depends on the d only. It is depends on the d. D is the separation distance of the 2 point sources. D is the separation distance of the 2 point sources. Okay, therefore we have the with respect of the this value 2 E naught equal to the 1. 2 E naught equal to the 1. After normalizing, you can experience the maximum E field as well as the where actually the nulls will be occurs, where actually the maximum will be occurs. 2 E naught equal to the 1 and the D equal to the lambda by 2. D equal to the lambda by 2. We have the equation. We have the simplified equation, that is E equal to the cos of pi by 4 plus the pi by 2 into the cos pi. This is our argument. This pi by 4 plus the pi by 2 into the cos pi is the argument to determine the maximum field. Okay, pi equal to the 0, we have the maximum field, and the pi equal to the maybe the some other value. Okay, at the time we have the minimum field. With respect to of that, this argument we have the field. The pattern of the figure of the revolution, most of the radiation is in the second and the third quadrant, but the pi equal to 0 and the pi equal to 180 degree. Consider here, observe this, pi equal to 0 as well as the pi equal to the 180 degree. On this axis, x-axis, that is the positive x-axis as well as the negative x-axis, the field is same. Pi equal to the 0 and the pi equal to the 180 degree, the field becomes the same here. Will be the same here. And you are setting the argument this, that is the pi by 4 plus the pi by 2 cos of pi m, which is equal to the k pi. For the k equal to 0, 1, 2, 3, go as so on. For the k equal to 0, it will be the pi m becomes the minus 120 degree and the 240 degree. Here the maximum radiation from the x-axis. At the 120 degree, we have the maximum radiation. At the 240 degree, we have the maximum radiation. Understand here how best you are setting the argument of that inside the bracket. Okay, for the maximum value, for the null value, you will get the phase pattern, you will get the field pattern. Suppose we are considering the spacing. Just now we consider the spacing between the two antenna will be the lambda by 2. Now the spacing will be reduced to the lambda by 4. Spacing will be reduced to the lambda by 4. And how the field is appears in the far field distance? How the field will be appears in the far field distance? Why? Because we have the equation dr equal to the 2 pi by lambda into the d, which is discussed in the previous lecture. Therefore, you substitute the d will be the lambda by 4. D will be the lambda by 4. What will be the equation? What will be the equation for the dr? That will be the pi by 4. That will be the pi by 4. Therefore, the equation will be becomes in the E equal to the cos of pi by 4 plus the pi by 4 into the cos of pi. This is our argument. This is our argument. Okay, here the separation distance will be the lambda by 4. Then based on this, the field, where actually the field will be the maximum. Where actually the field will be the maximum. Again, you have the setting of this equation, that is pi by 4 plus the pi by 4 into the cos pi, which is equal to the maximum. Maximum value, it will be the k pi. We have the maximum will be experienced at this particular point, but the at this source, at this point, it will be the 0. It will be the 0 on this x-axis. The field is experiencing will be the 0 on the x-axis. 0 on the x-axis. The direction of the maximum E field is determined by the phase of the source 2. Phase of the source 2 is 0 and the phase of the source 1 is 270 degree. The vector to right to vector to down is shown in this figure. Okay, vector to right from this source 1 as well as the source 2. Okay, the phase of the source 1 is 270 degree, is nothing but it is the vector to right to the vector to the down. Okay, means at the right side, by considering of this point source, it is with respect to of the 90 degree as well as with respect to of the 270 degree. Okay, vector to right is with respect to of the 90 degree as well as vector to down is with respect to of the 270 degree. That is shown in the figure. The field will be appears here. Therefore, this is the special case with respect to of that the phase quadrature. With respect to of the phase quadrature, the separation of the two point sources will be the lambda by 4. Earlier it was the lambda by 2. Now it will be the lambda by 4. Again, the case 4. Case 4 will be the point source of equal amplitude and the any phase difference. It is the general case. The amplitude will be the same. The point source is having the same amplitude and the phase difference will be any phase difference. Let us consider the phase difference delta and the total phase difference will be the psi. That psi is the phase difference between the two sources. The source 1 as well as the source 2, and the phase difference in the far field distance, that will be the delta. The total phase will be the psi and the phase difference will be the delta. Source 2 and the source 1 at a distance point in the direction pi. Therefore, the psi we are considering it is the dr into the cos pi plus the delta. Delta is the any phase difference and psi is the total phase difference from the source 1 to the source 2. Therefore, the source 1 is the reference for the phase. Source 2 is the advanced in the phase by the angle delta. Understand here. The source 2 is the advanced by the angle delta. Source 1 is the reference. There is no phase. Source 2 is having the phase with respect to of the delta. Therefore, the total phase will be with respect to of the psi equal to the dr cos pi into the plus the delta. Phase of the field from the source at a distance point is given by the minus psi by 2. Source 1 will be the minus psi by 2 and the source 2 will be the plus psi by 2. Then the field will be here. Then the field will be the E equal to the E naught into the e raised to plus j psi by 2 plus e raised to minus j psi by 2, which is equal to the 2 E naught into the cos of psi by 2. the general equation E equal to the cos of psi by 2, E equal to the cos of psi by 2 by setting the argument dr, this 2 E not equal to the 1. We have the general equation E equal to the cos of psi by 2. Psi is the what? Actually psi will be the dr cos pi plus delta. Dr cos pi plus delta. And the one more case we are considering, it is the most general case of the 2-point sources. 2-point sources of the unequal amplitude in the practical design. In the practical design, okay, in the far field distance, this will be with respect to of the any amplitude of the point sources and the any phase difference of the point sources. The observed field in the far field distance, that is the general case, that is the most general case of the two isotropic point sources of unequal amplitude and phase difference. Here, let us consider the source 1 at the origin. Source has a larger amplitude and field at a distance r has a equal amplitude and the source 2 be the amplitude a into the e naught. Source 1 is having the larger amplitude and source 2 will be the at the maximum amplitude, it will be the a into the e naught. If the a equal to the 1, both of the amplitude will be the same. If the a is ranging from the 0 to 1, therefore the amplitude difference will be there from the source 1 to the source 2. Source 1 to the source 2, therefore the amplitude difference will be there. Why? Because a is lying in this range. At the distance r, the field is measuring at the distance r. This is the far field distance. The magnitude of the magnitude and the phase angle of the field is by with respect to of the this source 1 as well as the source 2. Therefore, E equal to the E naught is the common. In bracket, it will be the 1 plus A cos psi square plus A square sin square psi. Psi angle arc tan A sin psi divided by the 1 plus A cos psi. This is the phase. That is the tan of A sin psi divided by the 1 plus A cos psi. It is the any phase difference. Therefore, psi equal to the dr cos pi plus the delta and the phase angle is referred to with respect to of the phase 1. Therefore, the two sources are shown. The source 1 is at the origin and the source 2 will be at the distance d. D will be what you have taken, it is the lambda by 2 distance. Obviously, the practical consideration all the time it will be the lambda by 2 distance only. With respect to of this lambda by 2 distance, we have the field observation in the far field distance. Therefore, the total phase, will be appeared with respect to of the this pi. With respect to of the this pi, it will be the psi. Psi is the dr cos pi plus the delta. Therefore, by the trigonometric relation, we have the consideration at this point. The field observation, it will be the E naught and it will be the AE naught. The field observation. Therefore, the total E field will be here E equal to the E naught into the square root of the 1 plus A cos psi square plus the A square sin square psi into the angle arc tan of the A sin psi divided by the 1 plus A cos psi. This is the phase, the trigonometric relation, and the zeta is with respect to of the how the phase will be changing in the far field distance from the these 2 point sources. Okay, this is the angle we are considering here, and this is the trigonometry. Okay, therefore we have the E, that is the total E field will be observed here. This is the phase difference by this angle to this angle, and this is the amplitude observed at the far field distance. With respect to of that, we have the field difference, this is the most general case. Okay, next we come to the the pattern multiplication, which is also the very important discussions, how the patterns will be observed in the far field distance if the more number of the antennas will be whatever transmitting, or if the more the number of the antennas will be radiating, or if the more number of the antennas will be receiving. Therefore, how this will be becoming the multiplication of the those all the pattern. If it is a sine and the cos, therefore the multiplication of this pattern will be observed in the far field distance. If it is the cos pattern of the multiplication of the two sources will be observed in the far field distance. Like this, it will be multiplied. Those amplitude will be gets multiplied, and those phases will be gets added. Those phases will be gets added. That is considered as a pattern multiplication of the sources. Pattern multiplication of the sources of the non-isotropic, or it may be the isotropic. We are considering it is the non-isotropic here. Non-isotropic is nothing but it is with respect to of the radiation. Okay, radiation. The total pattern of the any array of non-isotropic but similar point sources is the product of the pattern of the individual source. Is the product of the pattern of the individual source and the pattern of the array of isotropic point sources having the same location, relative amplitude, and the phase of the non-isotropic point sources. Understand here, the total field pattern of the an array of non-isotropic but the similar sources is the product of the individual sources pattern and the pattern of